Hello, everyone. Good morning. Thank you, everybody, for being here. For me, it's really a honor. It's my third time in Russia, and every time I come, I meet, brilliant researchers. It's very motivating. I think this is one of the most active communities I ever saw. I really appreciate that. Uh, So today I'm here to talk a little bit about security research, some of the challenges that I see, some of the trends that I believe are happening right now, and some of the problems that we have with mitigation development, with sharing learnings, and with bringing more and more of the community together. Just a quick disclaimer, even though I do work for Intel, I'm basically sharing my opinions and my ideas. Obviously, I try to bring those ideas also to the company, but that doesn't necessarily mean anybody on the company agrees with them. I do have some phrases that, in my opinion, really define what hacking is about. So one of them is I really believe hacking is still an art, and as an art, essentially we have poetic license. So I will make a lot of use of generalizations. I don't mean to offend anybody. If you feel that you were a victim of a generalization, know that I understand there are a lot of exceptions. But I still trying to talk about the mass and the whole community instead of specific cases. Also, I really believe that hacking is all about understanding. As more as you know about something, as more as you can modify that something, as more as you can explore that something, as more as you can use that something for other purpose. And that's what hacking is all about. So every time that I try to say, hey, we're gonna hack something, it's basically, hey, how do we learn more about that something? How we expand the horizons on that field. The objective here is not really to try to teach anyone, right? I really believe many researchers in the audience are much more experienced than me, and probably would have a lot to teach me, and I really appreciate that exchange. I'm just basically trying to give some ways of rationalize about mitigations and mitigation development and some of the challenges we face in this field. Hopefully, people will like some of those ideas, and we'll use them in conversations, and we'll use them in discussions, and we'll bring that to companies and universities. And even if you don't agree, at least there is a point for arguing, right? So I like the idea of having things that we can talk about. But if I really need to define the objectives of this talk with only one image, I would basically use the God mode from Doom. I don't know if anybody here is remember the game, but as someone who never been good at playing games, I always try to hack them and basically find other mechanisms that I could abuse so I could win, right? And the God mode is the perfect example of how researchers many times feels, right? Researchers are analyzing something, they write an exploit, they find a vulnerability, and they feel that they are invincible. Right? They feel that they are the best and the smartest asses in the world. And I am like that as well, okay? Every time that an exploit works, you have that thrill, right? That's what keeps us moving. Then when you start the next time, you know you will spend months trying to exploit something, but it's still, the thrill when you manage to do it is too big. We are addicted to do that, right? But this is also a problem, because many times when we're discussing our achievements, we fail to talk about the state of the art. We fail to talk about the improvements that exist in an area, all the other challenges that are coming, and all the other scenarios that maybe we did not need to consider for the specific case we were exploiting. So I think every researcher is a little bit of a victim of the God mode. At the same time, it's interesting because when researchers are developing mitigations, they actually have the opposite of the God mode. They really believe the attackers are idiots. Right? Because it's funny, because their mitigations always work, they raise the bar, they create something that is impenetrable, somehow always have the advantages over everything else that was created in the world. And this is actually what is creating a huge disbalance, right? In one side, when we actually exploiting, we always go and we say that we can do whatever. But when we actually write in the mitigation, we always assume the attacker can't do that much, and the attacker is actually stupid. No wonder why, again and again, the mitigations are failing. And then, I like this sentence by Alberto that basically says that the amount of energy that is necessary to refute bullshit is really a magnitude bigger than to create it. Essentially, that means that there is a lot of noise. Every time you go to a conference, every time you are in a company, every time you are in a university, and there are discussions around mitigations, discussions around security, there's a lot of people giving a lot of opinions. And it's very hard to differentiate which opinions matter and are based in science and fact, and which opinions don't necessarily matter and are just like exaggerations. We'll try to offer in this talk a way for us to rationalize about that. Hopefully it will be easy and simple. I like to say that other people also agree with that. So for example, Halvard Flake in one of his talks in Oxford, he basically shared the mitigator, right? It raises the bar until no exploits can be seen. And basically, it shows the same feeling, right? Like people keep talking about raising the bar in security without giving any metrics of what really raising the bar means. How do you really evaluate that something is an improvement versus that something is just added complexity? So this is a big challenge, and I think many people are seeing this as a problem in our field. When I give a talk, I like to start with hey, the points that I hope that everybody remembers from this talk. And I will have 3 points, and that's only 3 points that if you get out of here today from this talk and remember them, I will be happy. I will actually use the entire presentation to basically re-emphasize those 3 points, but they are only 3 points, really. So one of them is basically, we know that threat modeling is mature, right? We know that the engineering process of creating secure software is fairly old. It's fairly mature and well understood. I'm not saying it's effective, okay? It's just mature. Companies, in theory, have references that they can follow to engineer secure programs, software, hardware, or secure systems. That doesn't mean, again, that it works. That doesn't mean that all the companies are doing it with quality, but the process does exist, right? And it's fairly mature. But we don't have exactly the same mature process when we're basically talking about engineering mitigations. And here I'm using mitigations to talk about defense mechanisms that prevent entire classes of vulnerabilities from being exploitable, or that prevents unknown vulnerabilities from being exploitable. I'm not talking about the fixes that are individual for one instance of a vulnerability. That's the way that I'm using mitigations here. So why we don't have that mature process? I remember that when I was in engineering school, one of my math professors, he always made fun that the engineers do math a little bit different than the rest of the mathematicians, right? And I remember he was specifically making fun of the idea of the proof by induction of the engineers. So in the case of engineers, the proof by induction is really if it works for case 1, case 2, and case 3, it works for all cases, right? Which is obviously not what proof by induction is about, but I will take it. I will accept that if we're basically discussing mitigations. So why don't we try to create a rule and agree on that rule that is very simple? If you say that you have a mitigation for a class of vulnerabilities, that mitigation must work 100% of the time against at least 3 instances of vulnerabilities in this class. It needs to really prevent those 3 instances. If you're not able to find these 3 instances, you either don't understand the problem or your mitigation doesn't make much sense. It will only bring complexity. It's very hard to really believe that a mitigation is effective. So it's very simple. It's just 3. I'm not asking for 10. I'm not asking for hundreds. I'm not even asking for the majority of the cases. Just 3 cases. That would be a huge addition. So people would start saying, hey, it raises the bar. People would say, look, for these 3 cases, it worked. Another point that I want to say is that there's been a lot of work in formalizing what exploits are about, what is offensive research is all about. And I think this work is really, really important. I will talk a lot about some of the work and some of the research that is coming in this area in a minute. But I think that there is a big problem in the area is that sometimes people go and they understand the contents of a presentation or a paper about a given exploit. So for example, you come to OffZone and someone is presenting this nifty exploit that they wrote, and you really fully understand the presentation. It makes sense, right? You understand what is the vulnerability about, you understand how they come about exploiting that vulnerability, why it is a problem, you understand the impact. But that doesn't mean you are really able to do it. The only thing that proves you are able to do it is doing it. So I really like to say and to incentivize everybody to try. Don't just believe on the research that is presented. Go and do it. And as long as you start practicing it, you will see the other challenges that the researcher did not even mention in the talk. Because there was no time, because the researcher thought it was not important, and then you will really understand what exploit writing is about. So I really, really recommend people to really do it. On the topic of like, is writing exploits really an art, or writing exploit is really an engineering process? Can we really teach people how to do it and create a process in which we teach whoever that is like dedicate the time to learn? I really recommend doing like this panel that was held in New York University with many exploit writers and academics discussing it. So like if you're interested in going deeper on understanding if exploit is an art or engineering, I do recommend you to have a look into this material. But this is the point to remember, right? Those proposing mitigations, they need to understand the problem. Right? And to understand the problem, the only way is by doing it. If you never wrote an exploit for the class of vulnerabilities that you really want to propose a mitigation to, you're probably not proposing a good mitigation. Of course, you can also pair up with somebody who did it multiple times. But doing it is really important. So I would like to say that if someone proposes a mitigation and they never wrote exploits in this area, be very careful on believing on that mitigation, because likely the person don't fully understand the problem. So a good disclaimer here is that being able to write exploits and have written exploits doesn't necessarily mean you like to do it. Actually, one of the guys that I know that is one of the best ones in writing mitigations, he hates writing exploits. He thinks it's like an exercise in futility, right? But anyhow, he's able to do it, and he did it multiple times. Right? So I just wanted to be sure that everybody understands that. Also, another problem that I see is, and it's connected to the second point that I made, is us researchers, when we present something, there is always a limited amount of time, right? When you present a research work, like something like, for example, you wrote an exploit, like either like you're presenting a blog post, a paper, it could be academic or non-academic, or a presentation in a conference, time is limited. The amount of content you will share is limited. Sometimes you don't share something because you believe that something is not important. Sometimes you don't share something because you think it is so simple that everybody would know. Sometimes you just don't share because you don't understand really the problem, right? Like some parts of that problem, but you still manage to write the exploit and you still want to share the ideas there. So it is important that we don't create a misconception that a lot of people is really able to do that. Right now, there is a real problem on the amount of people that are able to do the offensive work. Like all the companies are struggling to find the talent. So, which is great for everybody who wants to do it. It's great for us because the market is really hot. There is a lot of opportunities. But it's also a problem because there is a lot of noise. There is a lot of materials that are being generated that don't really necessarily add much. And gathering information is getting harder and harder. Our systems are getting more and more complex. And basically, there is no enough time to look at everything. Every time you go and start to look into like a field inside the world of technology, you see how deep it goes. There is so much content, so much complexity that the time is just not enough, right? So we do need help. We do need to scale. But scaling is also very hard because usually practitioners don't necessarily like to teach. Right? And we don't necessarily like to document, right? And it makes sense. I mean, I like to break the stuff. I like that thrill. I don't like the thrill of writing a paper, right? And in the end, that creates even more challenges in our field. So the third point that I want to make is that as more as we know, as more as we see, we don't, and as more afraid we are on sharing. And then a lot of people are basically sharing even though they don't really fully understand the problem. And that only makes it even harder for us, right? So here's the thing to remember, right? Investments in defense, they need to be guided. They need to follow investments in offense, right? Offense learns and explore possibilities, new attacks, new scenarios, new implications. And defense needs to benefit from that. So the data really needs to flow, like the data really needs to be shared. Without offense, there would be no need for defense and vice versa, right? Offense is not more important than defense, but offense is really very important for defense. Otherwise, you don't really understand what you're trying to protect. So another problem here is it's very common that people believe that the details don't matter. Somehow, we created this idea that we are discussing high-level things, and the architectural points are what matters, but the details don't. But are the details that make all those mitigations broken. So the details do matter, right? And as as the details are shared, as better, right? Let's try to make that. So I will give some examples of things that I miss, right? Things that I look into the community, I look into the world, and they are very, very hard to gather, even though they look like trivial, right? One example is, for example, Pound-to-One happens, right? Pound-to-One is a competition, like hacking real systems. There is a bunch of companies that put their products there. This is really great. People go there and break those technologies. The media goes and say, hey, like someone owned, I don't know, Safari in 5 seconds. We all know it's not in 5 seconds, right? We all know that that researcher is likely working in Safari for a year. It's like find a vulnerability took a month to exploit it, found another instance of the vulnerability to get an info leak, took another month maybe to exploit it. So it was months of work, and there is an year or more of like studying to actually get that result in 5 seconds. And we'll get into that in a minute, but I think that like the write-ups that come after Pound-to-One and the presentations that come after Pound-to-One, they are very valuable. Like they share a lot of really important information on real life systems and real life like exploit cases that bypasses all the mitigations, few interactions from the user. And this has a lot of value. I saw a lot of people in our industry criticizing these presentations and criticizing the materials written there. Basically, folks are claiming that, hey, it's just another exploit. Why this is important? Well, it is important because if we don't share the data, first, others will not be able to know what is the state of the art. That's the very first element. Second, we would not know how our mitigations are failing. And without this data, how do we know we even need new mitigations? How do we know everybody proposed mitigations are not just looking for a promotion in their companies, and the mitigations are not necessarily useful or needed? We need data. So let's not only tell those researchers that their work doesn't matter, but let's incentivize them to share even more. One thing that I would like to see when they share this work is data regarding amount of time. Like how long it took, how long they are looking to this target, like what they already knew. Did they have any of the primitives already? How they found those bugs, right? All this data is very valuable when you're actually trying to engineer the defenses. And unfortunately, in many cases, researchers don't share it. And I think they don't share because they don't really see how valuable this data is. But I would love if they share. I want to prize Microsoft actually here. Unbelievable as it is, Microsoft is one of the companies that has been sharing this data. They have been presenting and trying to say that, hey, the rationale behind this mitigation was because of this number of exploits affecting this class of vulnerabilities. And that's been great. I think this is very valuable, and I hope like more start doing it. It's still on talking about like data that like looks trivial, but it's not easily available. Just a simple exercise. Metasploit has a lot of public exploits, right? It has a lot of vulnerabilities that people spent a lot of time writing exploits for them. They have like quality control, like fairly good quality of the exploits, some of them very good quality, right? But still, how do you know how many of those exploits bypassed which mitigations? Even though they do have tags for some of the mitigations, some of them don't even apply. So for example, they might say, hey, there is an ASLR bypass, but the actual exploit is not really bypassing ASLR, it's really counting on a module that has fixed addresses. So it's not really an ASLR bypass, it's really ASLR is not fully enabled in that target. So there is, and more than that, how do you know if a given mitigation was enabled, if that same vulnerability could be exploited to bypass the mitigation and the researcher just didn't, or the mitigation just didn't exist, but it would be bypassable. Just this very simple data is already not available. And we're talking about public exploits in a very, very used tool that the community supports. And why it's not available? Because it's not just information gathering, right? It's not just about looking to the tags of the exploits, looking to what they do, and coming up with the conclusion. How do you really respond the question on, hey, would it be possible if the mitigation was enabled? How do you go back in the history and look into all these other vulnerabilities that there are exploits there and say, hey, if I had this mitigation, would it really have prevented it? But this data would be super valuable. And like in theory, it's easy, but it is really not easy to gather that. Another point is, I think there is a fallacy in security where everybody talks about defense in depth. The idea of defense in depth came from the military, right? In which if your defenses start failing, some elements of the terrain or some elements that you put there would block the advance of the troops so you can relocate your troops to defense. This doesn't exist really in computers. Think about when ASLR, CFI, Canary, when that fail, it all fails together. While the attacker is writing the exploit, yes, the attacker needs to bypass one, find a new primitive, manage to bypass the other. But when the attack really happens, it fails all together. There is no such a thing as defense in depth in computer security nowadays. There are like some ideas, right? Yeah, you can try to put things on the perimeter, say that the perimeter needs to be on it, and you could detect, but detection doesn't really necessarily work. So when you really see something, then like it's already too late. But defense in depth does not apply for mitigations. So every time that I hear someone say, yeah, but this mitigation raises the bar and it's defense in depth, I really believe that person doesn't really understand what they're talking about. And that's why, you know, like when you go and you see the results of Punch 1, it's like 5 seconds and everything is gone, right? It's because, again, everything failed altogether. It was not like, hey, one piece of the failure and then the next piece and the next piece. Of course, there are some examples of cases in which defense in depth appears, right? I think the latest vulnerability in Exene is a perfect example, right? That it takes about a week for really exploiting the vulnerability. So it was an interesting example of defense in depth. Since I always like to prize the work of others, I also want to mention like Casey. She has been working and she's like one of the persons that created the idea, the whole idea of bug bounties. And bug bounties have been very important, right? I know that in many places, I am from Brazil, right? So places like Brazil, people make a really good living out of bug bounties. So bug bounties are important. It really brings more people to research and it does give opportunities to many researchers. But like the numbers there are all kind of doubtful. Like a lot of them, like the numbers that people claim, like, hey, there's 100,000 researchers registered. But from those 100,000, how many really received payouts? And how many can really live out of those payouts? Then you start like really seeing the reality that our field don't really have that many people working. Also, then like, what is the quality of most of those submissions, right? A lot of them are like really going out after the low-hanging fruits, things that should have been automated already. So it's really more about the maturity of the industry of defense than really on the quality and the number of researchers. Another like thing that I see in bug bounties is the companies themselves that are doing the payouts, they sometimes don't really have the maturity to do the proper triaging. So the companies themselves are paying for things that they should not be paying or paying more for things that they should pay much less due to the quality of the submission. So I think bug bounties are great, but at the same time, I don't really trust a lot on the numbers. I think we need much more researchers than bug bounties claim that they have. And that goes back to the importance of formalization, right? We thought basically being able to define what is about the work or like the offensive work, it's very hard for the academia to come to the state of the art, and it's very hard, we thought, the academia to really scale, right? Because the academics, they are like the source for the information, right? That's where a lot of the people, a lot of the talent comes in the industry. So if they don't really manage to get into the state of the art, we end up having a problem of scaling. And in security, that has been true for many years, right? Even though, again, I don't want to make a generalization. There are very, very good pools of like academics and academic knowledge. But overall, if you really look into the whole academia, the amount of students versus the amount of contribution, it's very low in security. So this trend of trying to formalize, trying to define what is an exploit, why something is exploitable, try to define things, it's been very, very important. Notice that here I'm talking about formalization, not as in formal methods, but really on defining things. Some of those are, of course, formal methods. Some of them are just like better explaining and putting it in computer science terms what an exploit is actually doing. A good example of this trend is, of course, the weird machine that was created as a part of the LangSec initiative. And I think this was very good. But then, if we look into these initiatives of formalizing offensive work, and for me, LangSec is one of the big ones, there is still, then, you start seeing that, then, why defense is failing, right? So I gave two examples where LangSec guidance and what we learned with LangSec basically opposes what people say in secure development. One of them is we know that in secure development, everybody talks about the rule of hey, the input must be checked as close as possible to the usage of that input. But that created what is this shotgun parsing that we see, where the companies and the developers, they mixing the input recognition with really just looking to certain values, right? And the input recognition end up spreading to the entire code, and that makes code really complex and make vulnerability understanding, exploiting and fixing really hard. That's why again and again we see companies failing to patch, right? Because they patch one instance, but there is many other code paths that come to the same vulnerability. Another place where secure development basically is in odds with what LangSec teaches is really on the intrinsically secure functions. Secure development talks about hey, every function needs to be secure by itself, so you can copy and paste code around and the code would still be secure. But we know that security is not really composable. So this property of just copying around and hoping that the whole system is secure, it's kind of like a misleading, even though the idea of the guidance makes sense. But just assuming that you will compose different components and it will still be secure, that actually is a failure per itself. As I said, right, there is many work coming out on formalizing that is not really LangSec. So some that I would like to cite is Sean Helen and Julian Vaneged, independently working on areas for formalizing HIPAA exploits. Sean is working on the automatic generation for HIPAA exploits. So he already has a paper out. There is more coming. And Julian worked on really defining a mathematical model of how HIP manipulations work. So both are very important, and I really hope that they keep moving the needle there. Of course, everybody here probably knows about the DARPA challenge on the automatic exploit generation, and that's becoming more and more trendy. So I really hope that more in the academia we will also get into this area. Sean is doing the work in the academia. He is in Oxford University, but he came from the industry. So I think it's the perfect example. Halvar Flake also released a paper recently, basically demonstrating and using a Turing machine to demonstrate exploit primitives and why vulnerabilities can be exploited using Turing machine, which for me is a fundamental work to bring more people from computer sciences into our industry. This list is not comprehensive, but one of the things that I always like to say is that we know we are in the right path if we look into other areas of sciences, and those other areas that have similar challenges end up coming with similar conclusions that we did. I always think that even though creativity is important, the collective genius is always the best, right? So if we're doing something too opposite, maybe we are wrong. So I was looking a while back into compression algorithms, and I had a problem that I needed to work on. And basically I came up with this blog post, which is a practitioner, and the practitioner basically talking about the compression and the complexity that exists in modern algorithms, and look into his conclusion. For him, a modern compressor is a bit like a compiler. The compressed data is a kind of program in bytecode, and the decompressor is just an interpreter that runs that bytecode, which is exactly the definition that LangSec gives, where data drives code, and therefore, a data recognition is very important for having code security. So for me, it's actually super interesting to see that in other fields, the practitioners are also coming to similar conclusions. As I said, the idea of the list is not to be comprehensive, but there are a lot of other work that try to define exploit writing. So in my opinion, the precursor, one of the very first work to really define exploit writing was by Gira, all the way back in the 2000s, in the beginning of the 2000s. And he was the person who defined the exploit primitives. So the idea is instead of looking into every case as, hey, here's a technique, and the technique works only in this case, he started trying to teach people on, hey, look into the primitives, look into what the vulnerability is basically exposing, and then you use that exposure to control and end up achieving the objective of the exploit. So I think this was a great work. As I mentioned, Microsoft has been doing a lot of good work on that, right? I think the openness that Microsoft has been showing with Hyper-V, for example, is impressive, right? They basically releasing the internals of the architecture, tools, and ideas on how the design works so other researchers can basically speed up and start working in Hyper-V faster than nothing, sharing like details on how exploits bypass the mitigations and all. And Dave Weston and Matt Miller have been also giving presentations on the mitigation strategy and the numbers that they see and what made them actually come up with some solutions. I really recommend folks to look into those materials because they are essential. I also had like a small stint on defining a little bit more about like exploit writing. So a while back, a professor of mine basically challenged me to define my profession with using set theory. And like the idea is like he's a mathematics professor. I was like an exploit writer, and basically like he basically wanted to challenge me. At the time, I didn't really give a lot of attention to the work that I presented, but along the years, many times when I was discussing vulnerabilities and was discussing mitigations, I used the model to explain it. And like some coworkers and I end up writing a paper recently to try to explain a little bit about this model. And I recommend folks to have a read on it, just in case you are interested in see other ideas there. But essentially, in our work, what we try to define is that exploit primitives can be combined together to get into an exploit objective, right? The exploit primitives that we defined, we use it from what Paxton has published that are the exploit primitives that they use. Today, in this presentation, I will show that this is not a complete list. Like I will show a case of a vulnerability that doesn't fit on the exploit primitives that are in this list. But it was like what was available at the time. I also believe that the exploit difficulty is something that is very hard for us to measure. So we try to use like a big O notation to try to define a complexity for an exploit. We also use the definition that Shai Geron and I used it for a talk that we gave. By the way, that talk was in Russia on probabilistic versus deterministic mitigations, where we try to make the case that encryption, if properly used, many times become a deterministic mitigation. But if it's not properly used, then maybe it is just deterministic, and you can break a secure solution based on encryption without necessarily breaking the encryption. I will give an example in a minute. So what is this new primitive that I mentioned that was missing in the work? And we called this primitive non-obliviousness. So what it really means. Imagine that you have a scenario where an attacker can see memory being modified. The attacker see that there is something that is going on without necessarily seeing contents. That attacker is blind for the content, but the attacker is not blind to the fact that the content is being played with or modified. Interesting enough, exploit writers have been abusing that. If you think about glitching, glitching needs to be done in a certain time. How do you know the exact moment? It could be a time-based analysis that you know after certain clocks you are in a given position of the execution, so you know you can glitch and win. But in a sense, you don't really know the content, but you still are not oblivious to the fact that you are there. Non-obliviousness actually exists when we start talking about memory encryption. And I will give an example of what is that. So imagine that you have a system where you have like the CPU core and caches with plain memory, like plain data. But every time that something goes to the main memory, it passes through an encryption device. And essentially in the main memory, the data is encrypted, while in the cache, it is not. So every time the CPU accesses something, the CPU sees the data as unencrypted. It's transparent to the CPU. But the main memory, the data is actually encrypted. Of course, there are many technologies that do memory encryption. So just to be very clear, I'm not trying to say about any Intel technology specifically. There are many technologies. I will give a list. Those technologies have all different implementations, and as I mentioned, implementation does matter. But this is a list of some of technologies that have memory encryption. Just so people understand that while everybody's talking about memory encryption in desktops and servers, this is not really something that new, right? So Xbox, Nintendo, the secure enclave processor in Apple, MEE in Intel, which does SGX, right? AMD is releasing solutions on that as well, right? So memory encryption is actually something super interesting because now, if an attacker somehow managed to read memory, the contents are encrypted. If the attacker modifies the memory, because the attacker don't have the key, there is an encryption that happens in the modification when the CPU will basically try to read. Basically, the data is decrypted, right? Since the data will be decrypted with a key that the attacker didn't know, in the end, the data is really random for the attacker. So look into how interesting. The attacker can see data being modified in RAM, because the data is encrypted, but the data is being modified, right? So you see that the encrypted data modified, but you don't really manage to see the actual data. You can change something, but you don't control the final value of the change. So it's actually super interesting properties that this created. And of course, like in the transparent encryption implementation, different technologies implemented it in different ways. Some of them use integrity and replay protection, like for example, Intel ME does, but that has a limitation. It's very hard to do it for the entire memory. Because where do you really keep the counters? Where do you keep your basically like tokens that guarantees the integrity tree is correct? And where do you keep the copy for the counter of the given area so you avoid replace? You need something like that. And if you're talking about memory with like multiple gigabits of memory, then the SRAM to keep all those trees gets too big. So ME has limitations. It ends up only protecting a small range of memory. Solutions that protect the entire memory, they don't use replay protection and integrity protection. So back in 2016, Shai and I, we presented like some attacks against like encrypted memory. And basically, just like to explain the attack in one image, the idea was like we found locations in code that first we were able to identify the location just by seeing the memory changing. Because the memory changed in a pattern that was enough for us to discover where the change was happening. And based in offsets in that change, because like now you have a block encryption, we were able to find the specific data that we wanted to overwrite. The adjacent data, so for example, in this case, we want to overwrite the pre-out flag. The adjacent data to that basically has content that you don't care about. So you can randomly overwrite it. And somehow, the comparison, in this case, the if there, is just like a not zero comparison. So if you overwrite with any random value, as long as that value you are not unlucky enough that the value ends up being zero, you win as an attacker. And you end up logging into the machine without actually using the password. So we showed this attack against like an encrypted memory, and it works, right? But of course, there is always a question when you demonstrate a new attack against a new technology using a completely different primitive, which is the non-obliviousness. The question is, can we fix this just by fixing software? In this case, obviously, this logging code can be improved, right? You could compare with the specific value, like flag should be 1, for example, and then the attack is gone. You could do these improvements straight in the compiler, and overall, over time, all the software would be improved at some point. So is it worth to do something better in the hardware? That's a really big question, and we need offensive research to actually be able to answer the question. So we kept looking into it to see if there is anything else that an attacker could do that is different than counting on these not zero comparisons and these overwrites that are random, but still the attacker wins. And basically, let's try to abstract a lot what is really going on and look more in a very simple picture. Basically, the memory, when you have like a memory encryption, becomes blocks of 128 bits. In this case, I'm assuming like the encryption is using AES 120. So the memory basically becomes blocks of 128 bits. So every time you touch something on a block, everything on the block changes. It's one of the properties of the encryption, right? Every time that the CPU fetches things, it gets into the plain memory. That's what the CPU sees. That's inside the caches, right? What can an attacker do? Is that different than the normal encryption for data at rest when you're using the data? And it just happens it is. Actually, if you really look into it, this block of 128 bits is actually very big if you think. Inside a block like that, you might have like multiple different variables of a given program. So for example, variable A in this example is an 8-bit variable. Variable B is a 16-bit variable. Variable C is a 32-bit variable. Interesting enough, if you flip a bit in variable B, it's going to flip in all the others in the block. But each variable is a different size. The chances for the flip to be something that the attacker wants, to be the final value the attacker wants, is based on the size of that variable, not on the size of the entire block. So if you really want to attack only variable A, and somehow you don't care about blocks, variable B, C, or anything else that is on the block, the chances for you to succeed is 2 to the 8. And now you start seeing that like even though you have encryption, it's 128 bits, just the fact that the data is not at rest, but the data is actually consumed, already changed the properties of that system. Brute forcing is actually very realistic in those scenarios. And then like we're like, okay, what is really a feasible brute force here? So you need to find like a data structure that has many different elements with different sizes. Hopefully one of those elements is of your interest, and the size is something that you can brute force. So for example, a 32-bit size, the brute forcing time is like 15 minutes. 32 bits is a good maximum size. If the other elements are changed, it doesn't really crash the system, or didn't really change the location or the state of that system. Because you want to brute force, you don't want every time you do it, if it crashes, usually those systems, because it's transparent memory encryption, what the systems do is, at reboot time, it regenerates the keys. So all the data is kind of gone and you need to start over, right? So you don't want to cause a crash. And you also don't remember the primitives, right? You have the non-obliviousness primitive. You need to have those primitives, right? You need to be able to write to the main memory, even though it's encrypted. You need to be able to write an arbitrary amount of time, anytime, and you need to be non-oblivious. Of course, having all that sounds possible, but the only way to differentiate theory from practice is finding at least one case that it applies. And I like a phrase by Noir. Noir is like an amazing exploit writer, and he basically, once he was looking to all the requirements to write a modern heap overflow exploit, and he basically asked if it's possible to basically cook a pie with all these ingredients, right? Because it's way too many requirements, so it looks sometimes that it's not realistic. But then we found an easy example, right? The Linux kernel, it manages processes using a structure called task struct. Those structures, they have elements that control the process, right? Inside them, one of the structures that controls basically the privileges of that process. And basically, for this privilege, it's a pointer to another data structure. This data structure is allocated by a small object spool that you can see that the allocations are happening. So you can find the allocations happening in memory. So you can find the location of your allocation if you're able to spawn the process multiple times. Given that, you acquire the non-obliviousness. You know the location, you know the changes, and you are able to identify the data you want to overwrite. And then, this is the data structure, right? So it's a bunch of 32-bit elements, and if you manage to brute force the effective user ID and get the effective user ID to be 0 at some point, you win. Since it's 32 bits, you have 2 to the power of 32 chances to actually win. The fact that the effective user ID is never tested for invalid values, doesn't matter what value you put there, the system continues. Your process continues executing, it will not just crash. So you can basically do the attack in 15 minutes and elevate any process on the system to be root. So the attack is possible, even though the memory is encrypted, even though there's a lot of limitations. The fact that the non-obliviousness property is there, the fact that all these primitives that I mentioned there, the arbitrary addresses, partially arbitrary content, arbitrary number of times, all of that is in the hands of this attacker, because the memory encryption is trying to protect against this attacker that can touch memory directly. This attacker is so powerful that memory encryption did not really block it. So, is it memory encryption really valuable or not? Or is Intel and AMD investing in technologies that maybe will not necessarily prevent the attacks that they're claiming it will? Notice that this example assumes that the physical machine access, but the memory encryption technologies, they also have these ones based on hypervisor, right? Where every time you change a guest to another guest, it basically changes also the encryption key. So one guest in theory would not be able to access the memory of another guest, even if there is a vulnerability. The hypervisor will not be able to access the guest memory, even though might be a vulnerability. It's exactly the same technology, the same principles of attacking it apply. There are limitations. The truth is, these technologies, they do raise the bar, but it's really, raising the bar enough here. Or those technologies need more. Without more research and more offensive work on this area to find the cases, to find the limitations, to see if those cases are super rare, or if those cases are really common and happening everywhere, it's very hard to define the effectiveness of something like that. Of course, like I work for Intel, right? I want everybody to go and go to the latest and most modern. But then, like, there are, like, it's not a panacea. It's not going to solve all the problems, right? More attack and more research is necessary. The world still needs to evolve, right? We still need the technology to be there. Otherwise, how more researchers will look into it, right? I was privileged enough to have access to early versions of the implementation, so I could basically look into it. But then, like, we need more people to look into those problems and how those problems affect us. And I think, then, like, without formalizing this process, without looking into what are the primitives, what a given mitigation really kills in terms of primitives, it's very, very hard to define how effective a given attack will be or not be against that mitigation. I think, you know, like, this is something important. Of course, you know, like, there are many other things that for this vulnerability to be demonstrated and to be exploitable that you need, right? You also need alignment. So, for example, either do like you were lucky and do like the target of your data is already aligned in a good way, or do like you need to find a data set that like doesn't matter the alignment. In the 128 bits block, you still always win because everything you overwrite there, other than your target for the brute force, will not matter. And in this case, like it does fit, okay? Like the specific attack does like work well against this data structure. And like once you define it, like what are the requirements, what are the primitives, what is the mitigation, and then you find the case. It's just a matter of like doing a simple table, right? You can go and look into what is the premise that you had for an attack to be successful, and then if the given case gives you those premises. And if it does, you know that that mitigation will not be effective against this attack, right? And in this case, you know, like as you can see, it's always a yes. Right, so basically, then, like we know that there will be possibilities for brute forcing attacks, and the attacker is still winning, even though you have memory encryption, right? So memory encryption is still helpful in many scenarios, right? If you have an accidental memory leak, an accidental memory overwrite that is not very well controlled, or it's just partial or adjacent areas, memory encryption would still like be interesting and would still be effective there. But there are cases where memory encryption will fail and basically will not give you the protection that in theory it would, people say. So I always say that like baby hackers are coming out of aliens, right? And like that's why like understanding makes so much sense. It's so cool, right? Because yes, like this research, as you notice, right, we presented the first version of the research in 2016. We started it really in 2015. And it's still nowadays in 2019, we are having new results and new findings, right? It does take time. A lot of the things that we did on the work were wrong. We went after like wrong ideas, wrong targets, couldn't find like cases that made sense, that were like really realistic, but then like anyhow, then like it's still worth it. But just to be clear, right, like the specific demonstration has a lot of limitations still, right? We basically assuming that there is a non-privileged software running inside the target that we can use it to control like the allocation. So we use it to control the spanning of multiple processes. So if somebody asks me how to make it even more realistic, this kind of attack, it would be, hey, find like if you can interact with a process like Apache or like a mail server like Nginx, a web server like Nginx, and like see if you can interact with it and force it to spawn new processes and still find that in an encrypted memory. So if you are able to do that, then you start having like the possibilities of like creating these conditions like through remote interactions and not with like a local interaction in the process. So there is still work to do for those attacks, but they are like an example of the importance of formalizing, of like going for the objectives, of looking to mitigations in a different angle, and basically coming up with the limitations that they have. Just like to conclude, and by the way, I will show a video of the attack working while we open for questions. But just so we don't forget the 3 points, right? The main 3 reasons were like I wanted to give a talk and I wanted to talk to you. The first one is like a mitigation needs to at least solve 3 cases, real cases in the past, and it needs to solve fully, right? It's not like hey, it blocked the actual exploit. It needs to make the actual vulnerability unexploitable at all. At least 3 of those. So let's try to enforce that. The second one, those proposing a mitigation, they really need to understand the problem, right? The understanding can be obtained in 2 ways and only 2 ways, in my opinion at least. One is actually writing exploit for the classes of vulnerability you're trying to propose a mitigation to, or pairing with someone that has a track record of doing it. Anything else, in my opinion, will end up being mitigations that only add complexity and don't necessarily solve the problem. And basically, of course, this also brings the point that we need to be careful with the new primitives, right? Because many times when a technology changes too much, new ways of attacking it appear. I like to use the example of SGX, right? SGX, before Intel released SGX, it was very rare that an OS would be considered an attacker to an application in user mode that the OS controls all the resources. Right? It was not normal that. SGX basically changed it. But because SGX changed it, it also brought completely new attacks that before that nobody thought about. I really like the work by Microsoft Research against SGX, where they basically forcing paging out to basically detect parts of the program that are running. That was super interesting. And that shows that every time a new technology comes and it's really disruptive, it also brings new primitives. So you really need to do an actual research on it. Just don't assume the world will not be changed by that. And of course, the last is the investments in defense. They need to be basically benefiting from the investments in offense, right? Just writing exploits and for marketing, which is a big part of our industry, uses exploits and exploit writing just as a marketing tool, is not really the best, right? The best would be if we can guide the defense and guide the improvement of the entire field by using the learnings and the offensive research. In the mitigation space, remember that the details do matter. Implementation details make all the difference. If you look into other papers released on attacking encrypted memory, many of them are really exploiting implementation problems and not really doing the full design problems we try to do. So I really thank you. I have some time for questions. I will let the video be playing and just before we open for the questions, essentially the video is showing two VMs, a victim VM and an attacker VM. Inside the victim VM, there is just a process that runs as unprivileged process. This process is only used to spawn multiple child processes, so we are able to locate in memory where is the data that we want to do the brute forcing. And then the attacker VM is connected to the debugger stub on the hypervisor. Remember here that because there is memory encryption between guests and the hypervisor and they use different keys, when I am in the hypervisor, even though I can connect to the stub on the guest, if I read memory or if I write into memory, there is encryption going on and I don't have the key. Right? So every time that I overwrite something, it's a random value, and every time I read something, it's basically encrypted garbage. But I still can do the attack, right? I can still do the overwrites and be no oblivious to the changes. And as you can see, once the attacker starts doing the overwrite after finding the location in memory, basically the values start being random values for the effective user ID of the target process. Of course, I printed as negative, but the effective user ID is unsigned, so it's just assume it's just a big integer. And the brute force goes on. Of course, the printing is not going for every try. The try goes into the millions, right? It's 2 to the power of 32. So there's a lot of tries that goes on. And basically, at some point, it just succeeds and you show the effective user ID with a 0.